Let's look at plate tectonics and volcanoes and how they relate. So we've got probably around 15 large tectonic plates spread around the globe, including our North American plate and the Pacific plate that's just adjacent to us. But all of these plates are formed within Earth's lithosphere. So that includes the outermost crust of the Earth, as well as the top part of the mantle, that's the asthenosphere. It's a gooey layer that underlies the crust in the uppermost mantle that these plates ride around on and create volcanism in certain boundaries. If we look at GPS data, global positioning system data, we can actually see and measure the direction and the magnitude of the movement of these different plates. And what you see here are arrows indicating the direction of movement. Let's say the Pacific plate there, that is moving west-northwest. And the arrow is quite long. That indicates the plate is moving faster than, say, the North American plate over here in the Western Atlantic. So those plate motions are driving volcanism, particularly in places where plates are spreading apart, as here, where these two plates are diverging from one another and creating a spreading center where they're diverging, at the point where they're diverging. We also get volcanism where plates are converging. For instance, in South America, where we have the Andes volcanoes erupting, where the Nazca plate is diving down underneath South America. So the magnitude and the direction of those plate motions are are dictating the kinds of plate boundaries that are generated, as well as the amount and location of the volcanism on Earth. If we look at the plate boundaries and a little bit more closely, you'll see on this map places where we have subduction zones. These arrows indicate one plate is subducting at another. The little barbs are on the overriding plate. So the Aleutian Islands are forming a volcanic arc where the Pacific plate is subducting beneath the North American plate. Or the Mid-Atlantic Ridge that follows the middle of the Atlantic Ocean, where the South American and African plates are diverging, where the North American and Eurasian plates are diverging, and there's volcanism taking place along there. So this map generally shows places where we have these mid-ocean ridges. Here, there's another good example where we have subduction zones, and I'll just use the ring of fire around the Pacific plate as a good example of where subduction zones are located. And there's a third type of plate boundary, and that's transform plate boundaries, which aren't terribly well represented here, but they include the San Andreas Fault, right where we live, and then sections along the mid-ocean ridges where there are little offsets along those mid-ocean ridges. And that's a plate boundary where we don't get volcanism. So just a little terminology as far as the structure of the Earth and to go a little bit deeper into what I just explained. I talked about the plates being comprised of the crust and the uppermost mantle. So on this diagram here, you'll see that the lithosphere, the oceanic lithosphere here, and the continental lithosphere over here are made up of just this thin crust, particularly found in the oceans, as well as the uppermost part of the mantle that is rigid. And so this whole thicker part of the outermost part of the Earth comprises the lithosphere, litho as in rock, and sphere as in sphere. And that lithosphere is riding around on this gooey asthenosphere, this layer that's a little bit deeper down, a little bit hotter, a little bit gooier, and deforming more plastically than the lithosphere. And the plates are moving around on that gooey asthenosphere. And then, as I explained, where we have plates converging, whether it's a divergent plate boundary where two plates are moving apart, and we see spreading and magmatism occurring at those spreading centers, where we have two plates converging, as in a subduction zone. Here it's a continent and an oceanic plate colliding, and the oceanic plate is being pushed down or pulled down into the mantle beneath the continental crust. And we have these transform plate boundaries, and they use the example in this diagram of one of these fracture zones between two segments of spreading ridge. And just to explain that briefly, if you've got two ridges, two mid-ocean ridges that are offset a little, it's not a perfectly straight line. We have one ridge spreading like this, another ridge spreading like this. Well, there has to be some kind of accommodation or deformation in between the two. And so if we draw on a line here, you'll see that this segment of the accommodation zone between those two ridges has to be a right lateral strike slip fault. So those are called fracture zones. Is a specific type of transform fault that's different from the transform boundary that we have in the San Andreas fault. So I want you to have these types of plate boundaries in mind as we go forward. I want you to recognize that we're going to be using terms like crust and mantle mostly, but I'll also use lithosphere and asthenosphere to denote the rheological differences in Earth's crust. So the lithosphere being the rigid outermost part of the Earth, the asthenosphere being the gooey layer in the upper mantle beneath the lithosphere. And those are distinct from compositional layers of the Earth, like the crust, which is a more intermediate in composition. Composition. And mantle that is ultramafic. So it's mafic plus. We can see several different kind of subsets of these plate boundaries at different places on Earth, and I'll just point out a few. I have mentioned the Andes as being an example of an ocean-continent collision zone, so where the Nazca plate is colliding with the South American plate, the Nazca plate, that oceanic crust is subducting beneath South America. That's distinct from an ocean-ocean collision zone where we have old, cold oceanic crust that's denser and gets subducted beneath younger, more buoyant oceanic crust. An example of where that happens and where we end up getting a volcanic arc or a chain of volcanic islands like the Aleutians. That also happens in Japan, and elsewhere where we have, in Indonesia and Malaysia down in here, we have oceanic crust, ocean collision zones. So those are different, and the landforms that we see and the type of volcanism that we see is going to be different in those two kinds of collision zones. We also talked about spreading centers, where oceanic crust is diverging, where magmatism is rising up and driving those plates apart. And that is different from a rift zone like East Africa. The East African Rift Zone, you know this area from probably from archaeology and where they found some of the earliest hominids in those rift zones. This is in a continent. It's not a plate boundary. It's perhaps a proto-plate boundary. It may become a plate boundary at some point, but it's a place where in the middle of a continent, we see magmatism that is driving intraplate motions. That also occurs in Western North America in the Basin Range. And so Nevada and Utah, that part of the country. Another another location that's also not at a plate boundary where we see volcanism are intraplate volcanism like Yellowstone and like Hawaii, where we have hotspots that have formed. And it's a hotspot in the mantle that rises up and gives us volcanism in the middle of plates. So Yellowstone there, Hawaii there. So they're not at plate boundaries, but a significant part of volcanism. So if we look where, just globally, where volcanism is taking place, you'll see I pointed out the Ring of Fire already around the Pacific Rim where we have many subduction zones. And there are places, island arcs in Indonesia that I pointed out, places in the Mediterranean. And you also see hotspot volcanism and Midocean ridge volcanism. But although this diagram doesn't actually point out Midocean ridge volcanism very well. And so the next diagram will show you where those ridges are. And you'll see that essentially it's encircling the globe through the Indian Ocean, through the Red Sea, around to the Mid-Atlantic Ridge in the Eastern Pacific, and into the Indian Ocean. That's a significant generator of volcanic rocks. And you can also see that in maps of the age of the oceanic crust. The red zones here are areas where new crust is forming, and those indicate young ages. And you see that, I'm going to choose a different color here so that you can actually see my writing. You can see that the ridge is at the center, and I'll just use the Eastern Pacific to start, and also point to the Mid-Atlantic, why not? The young rocks are symmetrical about those ocean ridges, those spreading centers, and that the age of the oceanic crust gets older as you move farther away from those spreading centers. And therefore the oldest ages for oceanic crust are somewhere around 160, 170 million years before it gets subducted, because when it gets old and cold and dense, it tends to be subducted beneath other continents. If we look at some images of the topography of mid-ocean ridges, there is a ridge. This image shows the ridge. It's not in the center of the ridge, but rather the high points are outside a trough where the volcanism is taking place. So the axis of the ridge is where the newest eruptions are taking place. Those rocks are then much hotter and more buoyant relative to the rocks that have moved away from that ridge axis. And as they get cooler, they get denser and ride lower on the oceanosphere. So the oceans become deeper, the oceanic crust is sinking lower down. And I've put some images in here. This is a lake that you can scuba dive in Iceland, where the mid-ocean ridge, the mid-Atlantic ridge, is actually exposed on land and then in this lake. And you can see features like, and this is in Iceland, this is the Wandafuka Ridge, this is near to us, but pillow basalts that are coming up, fresh basalts that are erupting and then forming these pillow forms because of the water that they're being extruded into. So what's happening in a mid-ocean ridge is that we have rising plume of melt in the mantle that's coming up at some point at these ridges, and we're getting extrusion of new crust, basalts, that form the oceanic crust and that are pushing the plate apart in this divergent plate boundary. We also have evidence, in addition to the ages that we see in the oceanic crust, we have these magnetic anomalies that point to this process, because we see symmetrical pattern of positive and negative magnetic anomalies that are recorded in the oceanic crust as it's erupted and crystallizes to form the oceanic crust, that record the north-south pole of Earth's magnetic system. And so a normal magnetic stripe would be like today, these black stripes, where the northern pole is true north, our current modern day north. And over time, it's flipped back and forth, and that's recorded in the rocks. So we have several places where we see typical features of volcanic rocks, including composite volcanoes, or they're also called stratovolcanoes. And those are the kind of volcanoes that you see when we have subduction zones. So convergent plate boundaries, here's an example near us where we've got oceanic crust, in this case of the Wandafuka plate. I just showed you those pillow basalts on Wandafuka Ridge. The Wandafuka plate is subducting beneath North America and giving us the volcanoes that include Mount St. Helens, Mount Rainier, that are near Seattle and Tacoma. And what happens in this process is that we've got this oceanic crust that has hydrous minerals, and there are sediments that are water rich that get subducted down the zone. Metamorphism takes place. They're metamorphosing those rocks, driving off water, and that water enters the overriding mantle and lowers the melting temperature of the mantle that's above it. And so it's actually the mantle, this mantle wedge that we call it, that then melts and generates partial melts of the mantle that rise up because they're hot and buoyant and enter the overriding continental crust and eventually make their way to the volcano where they're erupted. If we're talking about an ocean collision zone, what we see is that it's that older, denser, colder oceanic crust that's far from the ridge that is either pushed or pulled down a subduction zone beneath a younger, colder plate. So this would be a younger plate. And the same processes are taking place, really. But this time we're talking about oceanic crust. And so the composition of the oceanic crust is different than if we're putting melts from that overriding mantle wedge into oceanic crust that's overriding that subduction zone. And so actually the composition of the volcanic rocks that we get out in this island arc, or this chain of volcanoes that we call an arc, those are going to be different from an ocean-continent collision zone. And so what we're seeing is the same kind of volcanism, but we're seeing the chain of volcanoes emerging as the tops of these volcanoes are rising above sea level as those mountains are being built under the sea. So again, to point out that, you know, this kind of volcanism, this magmatism is taking place around, in large part around this ring of fire. So subduction zones generating the Andes Mountains, the volcanoes that are in Central America, our Aleutian Islands, the Japanese volcanoes, the Russian volcanoes on Kamchatka. We have the Indonesian and Malaysian volcanoes, and those down here in the South Pacific. Those are all part of this ring of fire where the Pacific plate and other smaller plates are being subducted beneath the plates that are around them. And so that's a significant proportion of the volcanism that's taking place globally. Those are generating these kinds of volcanoes. So these composite volcanoes or stratovolcanoes are these typical pointy peaked volcanoes that you imagine. I should have Mount Fuji on here as well. But these are the kinds of volcanoes that they generate. And the composition of the rocks that are coming out and the magmas that are being erupted is sort of intermediate composition. So the word andesite is actually named for the Andes, and that's an intermediate composition volcanic rock name. And so that's what's coming out of these volcanoes versus the basalts that are coming out at the mid-ocean ridges. We also see some more felsic volcanism, and this is Mount St. Helens. And there, this is sometime after the big 1980 eruption, where the side of the volcano was blown off or slid off. But we have a resurgent lava dome, that's this feature here, that is coming up. And that's a very felsic plug of lava that's being intruded. And so while in general those rocks that are the magmas that are feeding these composite or stratovolcanoes are intermediate in composition, we do see felsic volcanism, so rhyolites coming out too. Now, the counterpart to the stratovolcanoes are shield volcanoes, and then the lesser cinder cones that I'll show you now. Shield volcanoes are the kinds of volcanoes that we often associate with hotspots. And so this map shows many different hotspots around the globe, including Hawaii, including Yellowstone, Iceland. Well, that's a bit of a controversial topic there. The Galapagos, Easter Island, and other locations around the world. And these lines are showing the track of the plate across that hotspot. So the idea is that these hotspots are actually formed in a fixed position by a plume of partially molten mantle rising up and intruding into the crust above it, or lithosphere above it, and it's a fixed position. And the plates, earlier I showed you plate motions, indicating the Pacific plate was moving generally west-northwest, and that's the same trend as this part of the trace of the Hawaiian hotspot plume. And so that's showing you plate motions, and we can actually use the date the volcanoes along these traces of these hotspots and get an age for those volcanic rocks, and then use that to calculate a rate of motion for those plates. You'll also notice we can see historically there's been a change in the direction of motion of the Pacific plate over time. So that's interesting, including in the Nazca plate there with the Easter Islands and elsewhere. So as I've mentioned, these are mantle plumes that feed these hot spots, and so rising plume of mantle from a hot place in the earth, and that hot place where they arise is actually at the core mantle boundary. So this is an image of what it might look like, but it is literally the deepest, hottest part of the mantle, right at that core mantle boundary, that generates these giant plumes that rise up, and it's almost straight up in some cases, and then pond beneath the lithosphere and generate the volcanism that feeds these hotspot volcanoes. And in this example, it's Hawaii, and you see the motion of the Pacific Plate and this trail of islands that the hotspot has left behind. Now, these shield volcanoes are much larger than stratovolcanoes or composite volcanoes, and it may not seem like it because of their geomorphology. The nice pointy peak volcanoes that we think of, like Mount Fuji or Mount St. Helens or one of the Kamchatka volcanoes, actually they're much smaller in comparison to shield volcanoes. So there's Mount Rainier, a stratovolcano. Its size compared to the form of a shield volcano like Mauna Loa in Hawaii. The shield volcano doesn't have the pointy peaks. It's a much more gradual slope, but it's a larger volcano. The sheer size of it is much larger. So you can see the dimensions here. So 3 kilometers high, 6 kilometers wide versus 9 kilometers high, 50 kilometers wide. Or just the scale there. But I think you see the idea. So much larger. In fact, Mauna Loa is actually, if you measure from the seafloor where that volcano started its life, it's actually higher than Mount Everest if you were to compare the two side by side. So both of those, and these shapes, the pointy peaked intermediate composition stratovolcanoes are different from and have that different form because of the composition of the magmas that are creating them. Shield volcanoes are generally basaltic, and they're less viscous lavas and spread out farther and create more gentle slopes. Stratovolcanoes are more andesitic. Andesitic. And those are more viscous and don't flow as far. So viscosity is the resistance to flow. So honey is viscous compared to water. So the andesite lavas are going to be more viscous than basalt. And so you can get a steeper angle on the resulting volcano. Those are both quite a bit larger than cinder cones that can form in association with shield volcanoes or stratovolcanoes. They're generally basaltic, but they're very small features. And just look at the size comparison there of a cinder cone next to a stratovolcano. Here are two examples of Mauna Kea in Hawaii. Medicine Lake, which you may have never heard of, but we have a shield volcano in Northern California. And every other year I take volcanology to see parts of Medicine Lake. These are shield volcanoes, and these have a very typical shape of shield volcanoes. They're generally basaltic, with these not very viscous lavas that form them, and so shallow slopes. So imagine your basaltic lava. It flows very easily compared to the lava dome that I showed you, which is rhyolitic, that form a nice steep-sided little plug of lava. So these form those gradually sloping shield volcanoes. Here's another image of Haleakala and Maui, another shield volcano with those gradual slopes. Cinder cones in the caldera of Haleakala. So there are subsidiary features, they're small features, they're basaltic, and they generally erupt not violently, but can sputter and spit out scoria and other clastic material. Something that combines both aspects of basaltic magnetism and rhyolitic or intermediate magnetism is what's called bimodal volcanism. That means that you're getting both end members. You're getting everything from felsic to mafic volcanism. And that happens in continental rifts like East Africa and the Basin and Range province. So in East Africa, these continental rifts, remember these aren't plate margins. The plate margins are actually here in the Gulf of Aden and the Red Sea, where we're opening up small oceans. East Africa rift zone starts from in Ethiopia and stretches down into Tanzania, into Uganda, and there's quite a bit of volcanism that's taking place there that again is bimodal. So we're seeing both kinds of volcanism. The process of melting in a place like a continental rift is similar to what you see in a mid-ocean ridge, in that it's a place where you're thinning the crust, or you have very thin crust, and it's a place where the mantle can get very close to Earth's surface, and so there's not very much pressure on it, and that helps to partially melt the oceanosphere that underlies it. And we get intrusions of varying basalt, andesitic, rhyolitic material in those continental rifts because it's coming up through continental crust. If it were this wouldn't this kind of bimodal volcanism must be a result of this kind of these intrusions through continental crust, not oceanic crust, because it's the continental crust here that is changing the composition of the basalts that are coming out of the mantle. And I'll go into that process later on in more detail, but for now let's just leave it at that. So the Basin and Range is another place where we're seeing this rifting, and you can see the series of ridges and valleys across the Basin and Range, mostly in Nevada, but it spreads out into eastern Oregon, western Utah, and down into Mexico and southern California. And what we're seeing is there's basaltic magma coming up, ponding at the base of the lithosphere, forming magma chambers and erupting in various ways. So they might be a lava dome, it might be a cinder cone, it might be a lava flow that spreads out. But again, this is bimodal volcanism because it's coming through continental crust, in this case North America.